Formal notation of the indefinite integral. Good morning, class. Now, in the previous section, we spent some time understanding what integration is, how it essentially undoes differentiation. We saw how finding a derivative and finding an integral are like opposite operations. To be able to clearly and precisely communicate this process of integration, not just to each other, but to mathematicians all over the world, we need a standardized way of writing it down. Think of it like learning a common language for calculus. That's what this subsection is all about. We're going to introduce the formal notation, the specific symbols and terminology that mathematicians use to represent the indefinite integral. This will allow us to express integration in a concise and unambiguous way. We'll build on this notation in the following slides, so it's crucial you understand it thoroughly. We'll start by looking at how to write the integral, then break down each part so you know exactly what it means. So, let's dive in. Okay, so let's move on to a really important part of learning integration. Understanding the symbolic representation. Okay, so let's move on to formally representing the indefinite integral. As we discussed in the previous section, integration is essentially the reverse process of differentiation. Now, we need a way to write that mathematically. First, remember that when we're finding the antiderivative of a function, let's call it f of x, we aren't looking for just one function. We're looking for a whole family of functions, all those functions that, when you differentiate them, give you back f of x. This entire family of functions is represented by this mathematical expression. Integral f of x dx equals f of x plus c. Let me break that down. The symbol that looks like an elongated S, that's the integral sign. It's a historical symbol, and it visually represents the idea of summation, which is closely related to how integration is calculated. Everything on the left side, integral f of x dx, represents the process of integration, what we're doing. And everything on the right side, f of x plus c, represents the result of that integration. F of x is the antiderivative, the function whose derivative is f of x, and crucially, the plus c represents the constant of integration, acknowledging that there are infinitely many antiderivatives differing only by a constant. We'll delve deeper into why that c is so important in the next slides, but for now, just understand it represents that entire family of possible solutions. So, this equation is the core of how we express indefinite integrals, and we'll be using it constantly from here on out. We'll unpack each part of this notation in even more detail on the next slide. Breakdown of key terminology. Let's start with the very first component. It states, to master integration, it is essential to understand the specific role of each component in the notation integral f of x dx. Now let's look at each part individually. First, we have the integral sign. It's that elongated C symbol. We pronounce it simply as integral. This symbol is essentially an instruction. It tells us to perform the operation of integration. Think of it as saying, hey, find the integral of what follows. Next up is the integrand. The function f of x, that's what we're integrating. We call this the integrand. Remember, this function represents a rate of change, or, more fundamentally, it is the derivative of some original function that we're trying to find. Now let's move on to the variable of integration. This is represented by dx. It tells us with respect to which variable we are integrating. This is really important. Imagine you have a function with multiple variables, like x and y. The dx specifies that we're integrating with respect to x, treating y as a constant. If we were integrating with respect to y, we'd write dy instead. Following that, we have the primitive or antiderivative. This is the function, f of x, that we're ultimately trying to find. It's the function whose derivative is equal to our integrand. F of x, we can write this as f prime of x equals f of x. In other words, if you differentiate f of x, you get back f of x. Now, you might remember from our earlier discussion that the derivative of a constant is always 0. This leads us to the constant of integration, denoted by c. Because the derivative of a constant is 0, there are infinitely many possible antiderivatives that differ only by a constant. So, we always add plus c to our result to represent all possible vertical shifts of the function. This ensures we capture the entire family of antiderivatives, not just one specific one. Finally, the last bullet point simply defines integration itself. It's the actual mathematical process of finding this integral, this antiderivative. Okay, so now we're diving deeper into the notation of the indefinite integral. As we discussed on the previous slides, integration is essentially the reverse of differentiation. To really get comfortable with it, we need to break down exactly what each part of the integral notation means. This slide will do just that. Understanding these components is crucial. In the next slide, we'll see how this notation is applied in a practical example, and we'll also discuss some common mistakes to avoid. So, make sure you have a good grasp of what each of these terms means before we move on. Conceptual analogy, reverse engineering. Okay, let's move on to slide 4. This slide aims to give you a more intuitive grasp of what's happening when we perform integration, moving away from just the symbols and towards the meaning behind them. So the first point here says, to understand this notation intuitively, think of integration as reverse engineering. Now, what I mean by that is, usually when we differentiate, we start with a function and figure out its rate of change. Integration is doing the opposite. We're starting with information about the rate of change and trying to find the original function. It's like taking something apart to see how it works, but in reverse. Next, it says, imagine you are given a blueprint that describes how a building's height changes at every single point, that is, the derivative or the integrand. Think of a blueprint not as showing the building itself, but as a graph showing how the height of the building changes as you move along its base. This graph is the derivative, or what we call the integrand, the function we're integrating. It tells us the rate of change of the building's height. Then, it states, the process of integration is like using that blueprint to reconstruct the actual building, that is, the original function. So, if you only had that graph of height changes, integration is the process of figuring out what the building actually looks like, its overall shape and height at any given point. We're essentially rebuilding the function from its derivative. Finally, it says, because the blueprint doesn't tell you where the ground level starts, that is, the starting constant, you add c to account for the possible elevation of the foundation. This is a crucial point. The blueprint only tells you how much the building is changing in height, not where it starts. The building could be built on a hill, at sea level, or even partially underground. The constant c represents this unknown starting height or vertical shift. That's why we always add plus c to our indefinite integrals, to account for all possible vertical shifts of the original function. Now, keep this analogy in mind as we move forward to slide 5, where we'll see how this notation applies to a specific example. It will help solidify your understanding of each component. Step-by-step example of notation application. Okay, so now that we've covered all the components of the integral notation, let's solidify our understanding with a practical example. We're going to find the indefinite integral of the function f of x, which is equal to 3x squared. Now, step 1 is to write the problem using the formal notation we just learned. Remember, the integral sign tells us we're finding the indefinite integral. So, we write integral, and then we put our function, 3x squared, inside, and finally, we add dx to indicate that we are integrating with respect to the variable x, so it looks like this. Integral of 3x squared dx. Let's break that down again. 3x squared is what we call the integrand, it's the function we're integrating. And the dx tells us we're integrating with and respect to x. Step 2 is to identify the antiderivative. This is where we need to think backwards from differentiation. We ask ourselves, what function, when we take its derivative, gives us 3x squared? If you recall your power rule for differentiation, you'll remember that the derivative of x cubed with respect to x is 3x squared. So, that means our antiderivative, which we denote as f of x, is x cubed. Finally, step 3 is to apply the general solution formula. Remember from our earlier discussion that when we find an indefinite integral, we always add the constant of integration. See, this is because there are infinitely many functions that have the same derivative. So, we take our antiderivative, x cubed, and add c. Therefore, the indefinite integral of 3x squared dx is equal to x cubed plus c. And that's it. We've successfully applied the formal notation to find an indefinite integral. Keep in mind, as we'll discuss on the next slide, it's crucial not to forget that constant of integration, c, or the dx. Those are common mistakes students make. But now you have a solid foundation for tackling more complex integration problems. Common mistakes to avoid. First, and this is very common, is omitting the constant of integration. See, a lot of students will correctly find the antiderivative, but then write, for example, that the integral of 3x squared dx equals x cubed. Now, remember from our earlier discussion, integration gives us a family of functions, not just one. The derivative of a constant is always 0, so there are infinitely many functions that could have a derivative of 3x squared. By leaving off the plus c, you're only representing one specific function within that family, and you're losing the general solution. So, always remember to add plus c to your answer. Next, we have ignoring the variable of integration. It's surprisingly easy to forget to write dx after the integrand, but the dx isn't just a formality, it's crucial. It tells us with respect to which variable we are integrating. Think of it this way. If you have the integral of 2x die, that's different than the integral of 2x dx. In the first case, 2x is treated as a constant because we're integrating with respect to y in the second case. 2x is the function we're integrating with respect to x, so always include dx to clearly indicate your variable of integration. Finally, let's talk about confusing the integrand with the result. It's easy to get these mixed up. Remember that f of x, that's the integrand, is the input to the integration process. It's what we start with, and it represents the rate of change or the derivative. And f of x, the antiderivative, is the output. It's the original function we're trying to find. So keep in mind that f of x is the input, the derivative, and f of x is the output, the original function. Okay, let's move on to slide 6, where we discuss some common mistakes students make when working with indefinite integrals. It's good to know these up front so you can avoid them in your work. Avoiding these 3 mistakes will significantly improve the accuracy of your integration work. Now, let's move on to the final slide, where we'll recap the key takeaways from this section. Key takeaways. Okay, let's recap everything we've learned about the formal notation of indefinite integrals. This is really important, so pay close attention. This slide summarizes the key takeaways from this entire section, so it's a good place to solidify your understanding. First point, the notation integral f of x dx represents the indefinite integral of f of x with respect to x. Let's break that down. Remember that elongated s symbol, that's the integral sign. We said it represents a summation, essentially, we're undoing differentiation. So when you see that symbol followed by a function like f of x and then dx, it means we're finding the indefinite integral of that function. The dx part tells us with respect to which variable we are integrating. Next, the result of an indefinite integral is always a family of functions, denoted by capital F of x plus c. This is crucial. We're not looking for just one function. Because the derivative of a constant is always 0, there are infinitely many functions that could have the same derivative. That's why we represent the result as f of x, which is the antiderivative, plus c, the constant of integration. Think of c as representing all possible vertical shifts of the function. Moving on, the term f of x is the integrand, and dx specifies the variable of integration. We've already touched on this, but it's worth repeating. F of x, the function inside the integral sign, is called the integrand. It's the function we're actually integrating. And again, dx tells us we're integrating with respect to the variable x. If it were dy, we'd be integrating with respect to y, and the answer would be different. Finally, the constant c is mandatory in indefinite integration to account for all possible antiderivatives. I can't stress this enough. Leaving out the plus c is a very common mistake. It means you've only found one possible antiderivative, not the general solution, which includes all possible vertical shifts. So, to reiterate, mastering this notation is key to successfully tackling integration problems. Make sure you understand what each part represents, and remember to always include that constant of integration, c. In the next section, We'll start applying these concepts to solve more complex integrals, so make sure you're comfortable with this foundation.